I'm Campbell Harvey, professor of finance at Duke University. I'm very pleased to have Mike from Ethereum Foundation talk about separating MEV and staking. It's interesting, the hat that you're wearing, I noticed, was from the Ethereum Foundation retreat in June in Sonoma. And I was fortunate to be there. And I noticed that one of the main topics of conversation was the MEV. And it's great that you've got a presentation on this, and we're looking forward to it. So we're going to go for 1 hour. We've got a hard stop at the top of the hour. And the idea is that Mike will do the presentation, and we'll have clarifying questions or detailed questions in real time, then maybe deeper questions at the end of the presentation. So if you do have questions, put them in to the Q&A. So the chat is disabled. It's really hard to juggle the Q&A and the chat at the same time. Please put them into the Q&A. So Mike, thank you for making the time for us, and we're really interested in your presentation.
Yeah. Hey, everyone. Thanks, Cam. And thanks to Fahad for inviting me. Hopefully you all can see my screen. Definitely stop me if anything goes wrong. Yeah, as Cam mentioned, I'll be talking about separating MEV and staking rewards. So this is kind of from the perspective of Ethereum validators, who are the participants in the Ethereum consensus mechanism. How can we decouple these rewards? How do we think about them in terms of both the kind of micro level decisions validators make and the macro around ETH asset? So yeah, let's just jump right in. Cool, good to go. Wait, 1 sec. Zoom is slightly off there. Okay, hopefully the screen is visible. Yeah, so a quick sketch of the talk today. We're going to start by just going through a validator reward taxonomy. So again, validators are the participants who are responsible for creating and voting on Ethereum blocks, and kind of going through issuance, transaction fees, and MEV or MEV, the kind of main sources of rewards for the validators for participating in this production of Ethereum blocks. Then we're going to go into what I'm calling a mechanism toolkit. So first, we'll kind of motivate the reason to change. Like, we have the system running today. Like, what are the problems with it that could incentivize us to change something? We'll talk about MEV burn, which is a real-time block auction. And we'll kind of dig into the details of what it means to be a block auction versus the kind of next point, which is execution auctions, which are ex-ante slot auctions. So kind of the distinction between the two will be important, and hopefully will be made clear. And yeah, we'll kind of talk about how these two mechanisms play off each other, and in particular, we'll focus on how they relate to the validator rewards. And then the third part of the talk will be kind of a broader zoom out on decentralization as the means to neutrality. And we'll talk about kind of what neutrality means and how this discussion in particular fits in the bigger picture of Ethereum design, especially around transaction exclusion and digital property rights, which I think are the main focus of Ethereum. So cool. With that out of the way, let's kind of jump right in. And actually, before we start getting into the content, I thought it would be nice to just kind of do the related work up front. This has been a huge community effort. This talk and this line of research is within the Scourge part of Vitalik's roadmap, which is all about Ethereum block production, MEV kind of economics type questions. And so Barnaby, who leads the Robust Incentives group at the Ethereum Foundation, has kind of been a great KOL. This is a recent acronym I learned, which stands for Key Opinion Leader on a lot of these topics. And I'll kind of link some of the documents that helped contribute to this presentation and this line of work. Julian, Thomas, and Francesco have been doing a bunch of work on the inclusion list side. We'll talk a little bit about that. Terrence and Potes have done so much on the consensus specification, and they're kind of software engineers and researchers at the same time, which is super valuable. And then Elijah, Max, and Malesh, who have been talking a lot about concurrent proposers. This is a slightly different variant of the block production discussion. And I'm not going to dive too deeply into it today, but I thought it would be worth calling them out because it's been getting a lot of traction lately, and I think it's great to explore. Cool. Okay. The stage is set, right? So validator reward taxonomy, starting with issuance. So issuance is kind of the rewards that everyone's probably most familiar with when thinking about these blockchain systems, right? It's kind of the incentive that the network creates for validators to participate in their consensus. And the way that this is paid for is by creating new tokens or inflation. So, in Bitcoin, you create new Bitcoins every time you create a block. In Ethereum, there's kind of multiple ways that new Ether tokens are created. And well, I guess the kind of two main components are producing blocks and voting on the blocks. And the amount of yield that you get in the Ethereum network depends on the amount of stake, in the consensus mechanism itself. So the yield function is this sort of random, arbitrary looking inverse square root, but there's kind of a series of discussions around the parameters that were chosen. So I'll kind of defer the reader to this article down at the bottom. But the important thing to take away from this is that the amount of yield paid to a staker, so someone who has 32 ETH, who runs a validator in the Ethereum network, produces blocks, votes on blocks, helps keep the chain producing state updates and ordering transactions, depends on the amount of stake in the system. So there's about 120 million Ether tokens in existence. That's the total supply. And so this plot shows how the yield decays as the amount of stake increases. This is just the nominal yield because it doesn't account for inflation, right? So if all 120 Ether, all 120 million Ether was staked, then the real yield would actually be zero because everyone is earning, issuance at the same rate as the inflation, and that kind of wouldn't be as meaningful. And we're not going to dig too much into the kind of real versus nominal macro yield stuff, but this is kind of the main source of validator revenue comes from this curve here. And importantly, for this discussion is that these rewards are mostly from voting for the correct block. So as I said earlier, there's kind of this two-pronged thing where validators produce blocks and then they also are in charge of voting on them. And if you vote for the correct block, then you just say, hey, I saw this block on time. It was valid. The transactions in it execute. And I think it should become the head of the chain. I think we should update the state to include this block. Then you get rewarded for doing that. And the important thing here is there's not actually that much sophistication involved. It's just you're connected to the network, you're listening, and the blocks come in and you vote on them. And beyond just a relatively simple task for the validators, it's also the rewards you get are pretty smooth and kind of relatively predictable in time. As you see, this yield decays relatively gradually, and we've been kind of, the amount of stake that kind of flows in and out of the mechanism is rate limited. So you wouldn't ever jump from a 12% yield on the far left of this curve to a 2% yield over the course of a few days. That just wouldn't happen. It's a much more gradual approach. And so for validators, for people who are staking at home, and also for people who are staking in institutional settings, this yield is very predictable and something that they can depend on. Cool. So that's kind of the first piece of the puzzle. The second is transaction fees. Transaction fees are the amount users pay to interact with Ethereum. So if I want to send Ether to Cam, if I want to swap my Ether for USDC or for wrapped Bitcoin or something, then these are the kind of the fees incurred by the user in order to interact with the network itself. And these fees are split into two parts. This is from the EIP 1559 mechanism, which has a base fee. This is kind of a reserve price or a kind of minimum amount that you have to pay to get included in the block. And this is dynamically updated based on the current market demand. So we won't kind of focus too much on the exact details, but basically there's a posted price. I have to pay that posted price, and that's the base fee. And if there's a huge amount of demand, that posted price will go up 12.5% per block potentially. So it has this exponential increase until a point where it equilibrates and the demand matches the the supply. And then the priority fee is the second component here, which is beyond the base fee, beyond this posted price. I also can optionally tip the block producer for inclusion. So this is the kind of flow here is I'm a transaction originator. I type up, how much I'm willing to pay on my laptop. And I say, okay, the posted price is maybe like 0.01 ETH, but I really want to get this transaction in the next block. So I'm going to give another 0.01 ETH to the person creating the block in hopes that they'll include me right away. And so the reason we kind of bring both of these tips up in terms of the validator rewards is that the base fee is actually burned in this mechanism. So burned in this case just means you take that value and you destroy those Ether tokens. So for a validator, if they include a transaction that has a large base fee, it doesn't actually impact their like local revenue at all. Like that fee just goes and gets burnt. Whereas the priority fee is actually what counts towards their revenue. So I get actually tipped directly for including some set of transactions, and that's impacting my rewards. And so this figure from Block Native Gas Estimator shows this is just like a kind of a live view of some of the gas prices. You can see that in the kind of base case, the base fee is much larger than the priority fee. And that's because in general, like getting transactions included is not actually that difficult because there's a lot of space in the block, and most of the time people just kind of grab all the transactions that they see and stuff them in the block. However, priority fees do have extreme variability, and that variability comes mainly from the kind of market conditions and the demand created when there's congestion on the network. So if the base fee is 0.01 ETH, using the example we started with before, but let's say there's like way more than 30 million gas worth of transactions. That's the maximum amount of transactions you can put in a block. There's way more than that demanded. In that case, your only way to kind of signal extra interest in getting included is by including that priority fee. And this is, this is, okay, there we go. So this picture shows kind of just two random blocks I grabbed from yesterday. And on the left, you see how much gas is being used in the block. So this first block has 5 million gas being used. That's 17% of the total gas. Whereas this second block has 29 million. So 99% of the gas is used. And on the right, we see that the fees paid between these two blocks are super different, right? The first block is 0.01 ETH. The second block is 0.42 ETH. So there's, 40x increase in priority fees between two slots. So this is 12 seconds apart. So, just because I happened to be the proposer at one slot versus the next slot means I could have like a 40x improvement in the amount of fees I earn during that slot, which is like kind of a wild amount of variability. Right. And the third and final subset of validated rewards that we'll talk about today is MEV. This is an acronym. You've probably heard it, but it stands for maximal extractable value, or originally it was minor extractable value. And this is the value created from the ability to reorder and insert transactions. So the kind of the reality of Ethereum block production is there's 12 seconds during which a single block gets produced. And during that time, you kind of batch a bunch of transactions together into a block. Now, obviously, if you just order them in whichever ones you heard first, say, you kind of have one natural order that defines how the transactions could be sequenced. However, it might be in your best interest to sequence them in a different way. And the canonical example of this is something called a sandwich. So this is a dashboard from a group called Sorella that they recently launched this explorer that helps kind of see how these transactions get bundled together. And there's kind of a lot going on here, but the key takeaway I highlighted in purple at the top, which is, well, actually, let's focus first on the actual outcome of the sets of transactions. So at the beginning of the transaction, we see that there's 32,220 of these pickle tokens. So the person starts, this is just a random token. Like, I don't know this. I don't know what pickle is, but whatever. And after a set of many different transactions, I think there's about 12 swaps that take place. There's some transfers. A lot of stuff is happening kind of in between the starting point and the ending point. But at the end point, they have 39,453 pickle tokens. So over this course of, of the set of transactions, they're able to produce, just from arbitraging and balancing out these different pools, 200 more pickle tokens for themselves. Now it looks like the revenue that they got was about $8. So that's how much the pickle token was worth. To include that set of transactions cost them $7. So they have some margin. So this is just one set of MEV strategies. This is a very common one called sandwiching. But there's many other types. There's kind of these non-atomic and atomic and non-atomic arbitrages. These are examples where you're balancing prices between different pools on-chain, or you have an external off-chain trading venue like Binance or Coinbase, where the price is moving at a much higher granularity than it is on the Ethereum block. And so you have kind of a disparity in that price, so you can balance between the two. Liquidations are another example. So kind of all of these forms of MEV are produced during the natural life cycle of economic activity on the Ethereum blockchain. And very similarly to transaction fees, MEV is highly variable in market conditions. In addition to that, and kind of this differentiates it from transaction fees, it also differs in builder sophistication, right? So this example sandwich above has 12 transactions or whatever. And, these types of strategies that for these types of strategies that involve, large amounts of sophistication, you have to be running potentially bots on chain to look at the different pools. You might have to be tracking the price on an external venue. This type of behavior looks a lot more like high frequency trading or market making, or like these strategies that your average solo staker, someone who's just running their validator at home on their internet connection, doesn't want to do. So in that regard, this builder sophistication is like a big portion of where the MEV revenue comes from. Right. So a quick summary of all of our rewards. This is from the ultrasound.money website, and it kind of shows an estimated breakdown of what percentage of validator rewards come from each of these three things. So issuance is about 65%, tips 19, MEV 16. But this is an average, right? And in particular, during some high volatility periods of time, the MEV rewards could dwarf the yearly issuance. It could be like a 10 or 20 ETH block, whereas your issuance for the whole year might only be 1 ETH. So the key takeaways here: issuance is stable, not very gameable. Tips are highly variable, both in market conditions, or this is a typo, but yeah, it should just say in market conditions. And MEV is variable both in market conditions and the sophistication of the block producer. So that's kind of the takeaway. And one last kind of dashboard to take away this, to drive home this point, is from mevboost.pix. And this shows just the second two portions. So the MEV and the gas fees. Gas fees is another way to describe tips. And you see the blue bars are kind of highly variable over the course of a few days. This is the past few days. But MEV is just insanely volatile, right? So in this day on August 27th, there was 256 Ether worth of MEV generated. Just 2 days earlier, this is about 30 ETH. So there was a 10x difference in the MEV that you get if you're a proposer on August 25 versus if you're a proposer on August 27. So you can see kind of, and I'm alluding to some of these issues around kind of distribution and fairness of validator rewards, which will come up as we discuss why we might want to motivate a change to the system. Cool. Yeah. So to kind of jump right into that, what's the motivation to change? There's many centralizing forces around the extraction of MEV, but we're going to focus on two. And again, centralization is kind of this constant battle that the Ethereum ecosystem is fighting against to try and keep this credible neutrality, keep the permissionlessness of the asset. And we'll kind of talk about that at the end when we zoom back out to broader Ethereum design goals. But I guess for now, you'll have to take it on faith that part of the Ethereum design space is like trying to be decentralized. So in order to push back against that, this is some of the steps we could take to change the system. So the first is timing games, latency, and colocation. So this just is a natural byproduct of the fact that this is a financial system. And, the reality of financial systems outside of crypto is they operate on a microsecond and nanosecond time horizon, right? These trades, this is like very Flash Boys 1.0 stuff where, if you're the first person to know the price on CME and you're trading in the New York Stock Exchange or whatever, like you're going to be able to take advantage of that time, and time is very much money in all cases. The second is reward variability. And this is bad for the risk averse and infrequently sampled solo staker. So, even though the average of my solo staking rewards should be the same as what a pool averages, the issues run into the fact that I, as a solo staker, might be risk averse and might kind of prefer to join a staking pool that has kind of smoothed out a bunch of these rewards instead of taking the chance and rolling the dice on like a very high value but low probability outcome and a low value but high probability outcome. So, as a solo staker, I produce a block about once every 4 months, and all of my blocks have been like the 0.01 ETH kind, and it's kind of discouraging when you see that the pools get all of the upside of taking all of this MEV and all of the kind of high variability of the value that's created and captured by the stakers, and you get to smooth it out over everyone who's involved in the pool. So Coinbase runs 10 to 15% of the Ethereum network, so they get 10 to 15% of the MEV, and that's just smoothed over everyone who's staking through Coinbase. So it just makes the incentive to join that much stronger. Right. So before jumping into kind of the proposed set of changes, we actually first have to talk about what the model of block production is today. And this is something called proposer builder separation. And this was very much in line of, in the spirit of kind of bringing access to the MEV value to all proposers and all validators. So, in order for everyone to get access to the MEV, we have this mechanism called MEV Boost. MEV Boost is essentially an auction that takes place. The auction is conducted by a relay, and the relay allows proposers who are the people. Proposer is the name for the validator who is selected to lead a specific slot. So it's like, hey, it's your turn to create a block. The proposer says, hey, I don't know how to do all this fancy stuff. I don't know how to extract MEV and do this high frequency trading. So I'm going to sell my opportunity to do all this stuff to a builder. And the builders are going to bid in this auction to compete for the right to do this. So the kind of flow, very, very simple, is the builders send bids in this auction to the relay. So the relay is kind of the auctioneer. They're the trusted third party. The relay forwards the winning bid to the proposer. The proposer signs this bid. This signature is like a cryptographic primitive that ensures that if the proposer signs one winning bid, they can't sign a second one. So this gives the builders confidence that like, hey, my bid actually did win this auction, and the proposer can't equivocate on that promise that they made to me. And then the relay publishes the block. So obviously this abstracts a lot of details, but this is kind of how the flow works today. And kind of taking a step back and saying, okay, what does proposer builder separation do for us? Well, first, the relay brokers this fair exchange and allows all validators to participate in the MEV market if they want to. So the idea here is if you didn't democratize access to MEV, then only the most trusted and centralized staking pools like Coinbase, like Lido, would have access to this MEV. Sorry, there's 1 or 2 chats coming in. Oh, okay. These look like questions that I'll probably tackle after. Right. So yeah, all validators can participate in the MEV market if they want to. And it turns out that most people want to. So this diagram here, also from mevboost.pix, shows the percentage of Ethereum blocks that are built using this proposer builder separation gadget that I described in the previous slide. And you can see it hovers right around 90%. It moved into that regime, that like 90+% regime, immediately after the merge, which happened in September of 2022. So clearly, like, there's high demand for these validators who don't want to be in charge of sequencing transactions to outsource their block production to the builder market. However, there still are games to be played. Like, this isn't kind of done and dusted. We can't just say, oh, MEV Boost is the perfect system and we're going to leave it as is. One of these games is kind of displayed in this picture on the right. Again, this one's from Sorella Labs. And this shows the value of bids in this auction as time progresses. So the Ethereum validator who's selected to be the proposer has 12 seconds to propose their block. The kind of honest behavior is to propose it right at the beginning of your slot, essentially. And this diagram, it's shown as plus 12. Like this is 12 seconds after the previous slot ended. I'm supposed to be like, okay, or sorry, 12 seconds after the previous slot began is the beginning of my slot. I'm supposed to publish my block at the beginning of my slot and, accumulate the rewards from all the transactions leading up to that. However, you might be incentivized to wait a little bit longer to delay your block publication and earn extra rewards as they come in. So we can see this person waited maybe until 13 or 14 seconds into the previous slot and got like maybe 2 extra seconds of block rewards. And this is very PvP or very adversarial, because if you think about what's happening here, I'm kind of effectively stealing MEV from the next guy. This is a very zero-sum world where any time that I use of their slot is time that is not accumulating MEV and transaction fees for their own block. So there's still some amount of games going on here, and that's what we'll talk about as we look forward into the design space more. Cool. So now we're kind of into the real meat and potatoes of the presentation. So hope you're having fun. We're going to kind of outline 2 different mechanisms that address the 2 things that we pointed out before as potential problems with the existing PBS landscape. The first is this timing games and latency stuff. And the second is the variability of block rewards for stakers and validators. So this first proposal is called Payload Timeliness Committee in MEV Burn, and the kind of exact mechanics here are less important, and we're actually going to focus on the second half, which is the MEV Burn part, and we'll show how MEV Burn actually is a mechanism to try and smooth out the variance in block rewards between proposers. So how does this work? We have a very similar setup to what we have in the existing PBS world. We have the proposer on the left, the builder on the top right. Now, instead of the relay, we have this committee of people. This committee is just a subset of other validators. So this is very much in line with like how the proposer is selected. You just take a set. We have about 1 million validators right now. You just randomly grab one and you say, okay, you're the proposer. And then you grab maybe like 100 and you say, okay, you're in the committee. It's just a simple lottery that takes place. Now, the flow takes place like this. So the builder bids in this auction. It's still an auction. It's still taking place during the slot itself. So I'm the proposer for slot N. The builders are building a block kind of in real time. So my slot starts at t equals 0. 12 seconds have elapsed since the previous block was created. And by the end of my slot, or kind of the beginning of the next slot, my block has to be published and include some set of transactions. The builders participate in this auction by sending their bids both to the committee member and to the proposer. The proposer does this winning bid signature thing. This is very much in line with what was done previously, where there's kind of this commit reveal phase. So the proposer commits to something and then the builder reveals it. The commit reveal before was handled mostly by the relay, but in this context, we try and do it just through the protocol itself. So we don't have these kind of trusted relays sitting as middlemen. Now, an important bit here, this is kind of, I would say, the most important for our discussion, is this committee enforcement that the proposer selected a sufficiently high bid according to their view. So what does this mean? Well, the committee sees some set of bids that are coming in, and then eventually they see a bid signed by the proposer. And they say, hey, the proposer, to make sure that the proposer is like honoring this auction and like actually taking the highest bid, we're going to enforce that they chose a sufficiently large enough bid according to our view of the other bids in the pool that the builders were sending to us. And this is very important because that threshold is actually the amount of MEV that is, this is part of the revenue of this auction that's being generated. And we're going to say in this version, in MEV Burn, we're actually going to take that MEV and destroy it. So this is very similar to the base fee in the transaction fee portion that we talked about. So you just take that ether and you take it out of existence. So instead of flowing to the validator, to the proposer as proposer rewards, and validator, just pure revenue to that staker, we're saying, hey, this actually is going to be kind of destroyed. You don't necessarily have to burn it. You could also just smooth it among proposers for a recent epoch. So you could smooth it over like 32 slots, for example, or you could smooth it over a longer time horizon. And as you can see, like this is very much in the spirit of making this distribution of MEV more egalitarian, more equal among different proposers within slots that are close to each other. Right. The builders publish the block. This is kind of obvious as the second phase of the process. The builders have to actually produce the block, and kind of not super important for our purposes, but there is another role that the committee serves, which is enforcing that the builders block is published on time. So yeah, let's take a zoom back, a step back, and talk about what we actually did here. So as I described, it solves this in protocol fair exchange between builder and proposer. There's no trusted third party. The trusted third party is effectively the committee, which we assume has this honest majority property from being sampled from the validator set. And the main benefit here, in my mind, is that it aims to address high reward variability. And it does that by burning most of the MEV. So, you know, that plot that we showed before where it was like 300 ETH or 256 ETH of MEV produced on August 27th and 30 ETH of MEV produced on August 25th. That MEV is still being produced, but instead of going as value to the people who created those blocks, it's actually just being burned. So it's kind of being internalized by the network. But MEV burn does not address timing games and latency advantages. So that whole plot with the bids taking place past the point which the auction was supposed to be finished, that is not addressed here. And there's also incentives for proposers to co-locate with the builders, right? Like if I'm able to be running in the same data center, maybe like running on the same machine as a builder, then I know that I'm going to get their absolute highest value bid from their auction. And so there's still incentive for me to kind of take advantage of anything that I can do to be more fast and efficient in this auction. Cool. So that's MEV burn. That's the first thing I wanted to talk about. And again, the second issue that we want to deal with is this whole latency thing that we described, this whole timing games thing. And execution auctions is a proposal to try and address that. And so it's very similar to what we just saw. We have the exact same three cast of characters with a proposer, builders, and a committee. However, in this case, the proposer actually auctions off the slot ahead of time. So before, this auction was taking place during the slot itself. And what happens when when you do that is the actual value of the object changes dramatically at the beginning of the slot versus the end of the slot. So imagine if you're trying to sell a piece of art while the artist is painting it, right? Like, oh, I kind of like how it looks at the beginning, but then they did something I didn't like. So maybe my value goes down, but then by the end you see it's a masterpiece and everyone wants it. I don't know, reasoning by analogy or whatever, maybe slightly sketchy, but this makes it very difficult for the auctioneer who's trying to decide like when to sell their thing, because the object is changing dramatically underneath them. And you might really be incentivized to kind of play with abuse your role as the auctioneer as much as possible for your own profit. In this case, the proposer is actually selling the slot 32 slots ahead of time. So I'm the proposer for slot N. The thing that I'm selling is slot N plus 32, that block production. So obviously the builder can't commit to a set of transactions because we have no idea what transactions are going to come in the next 32 slots. However, you can still commit to a specific builder who now has permission to produce the block during that slot, no matter what they put in it. And when the slot comes, they don't have to do anything. They just say, okay, it's my turn. I won this block. I won the opportunity to create this block 32 slots ago, so I'm going to create it. You know, they've already paid the proposer. So if they don't show up, if they don't build the block, it's kind of their own problem, not the proposer's problem. They already got their check. And so that's kind of the incentive here. And we'll talk about why this is potentially beneficial as we go through the flow. So, right, very similar flow to what we have before. We have bids going from the builders to the committee and to the proposer. The proposer signs this winning bid. Again, this is this commit reveal thing. In some sense, there's not actually a reveal here until 32 slots later, though. And that's one kind of key component. And then the third bit is this bid thresholding. Very much in the spirit of what we did in MEV Burn in the previous slide, we have the committee saying, hey, these are the set of bids we saw. We're going to force the proposer to take one that's big enough, sufficiently large. And obviously there's sufficient here is kind of intentionally vague because it's a parameter. But yeah, that's the goal. And that's what we're getting at. So just to kind of hammer home the difference, the auction takes place 32. Again, another parameter could be any other number of slots ahead of time. And the bids do not commit to the block contents. So, okay, this seems kind of weird. Like, what are we doing? We're kind of moving the timing around. And from the high level, this is doing the exact same thing that we were doing before. We're allowing an in-protocol fair exchange between the proposer and builders. However, what we're trying to do is address these timing games and the kind of implicit or really explicit validator sophistication that is directly downstream of being the auctioneer during the kind of during the slot itself while the auction while the block is being produced. And Barnaby coined this term called the value in flight problem. I think it's a really nice way of describing it, which is the value in flight of a block during the slot itself is very high. It changes dramatically, but when you're selling a block very far ahead of time and there's much more uncertainty around the state of the world when that block will take place, there's much less value in delaying and kind of manipulating your role as the auctioneer, right? So you could imagine like I'm selling a block 3 minutes in the future or something, or 10 minutes in the future. The difference of the value in that block or the rights to produce that block for the beginning of my slot and 12 seconds later, it's still 10 minutes in the future, just 10 minutes minus 12 seconds. So almost 10 minutes in the future. So it's very less likely that I benefit dramatically from playing all these games and trying to be super sophisticated in my timing. So that's the kind of direct goal of execution auctions. And they also do reduce the validator rewards variability in the exact same way, which is this bid thresholding and ensuring that most of the MEV that is captured in this auction, most of the revenue generated by this auction is actually just destroyed or smoothed among everyone. However, this seems like a silver bullet. You're like, Mike, you asked for two things and an execution auction checks both of them. But they have this kind of key problem in my mind, which is they suffer from a much higher risk of multi-slot MEV and reduced builder competition. So Max and Malesh made this argument very concisely in this paper. I link at the bottom, but the kind of key takeaway here is if I'm a builder, I can buy slots in the future and I don't have to compete in a real-time auction once the actual slot comes to bear. So let's say I buy 5 slots in the future in a row, 5 back to back to back to back. Now I can do whatever I want. I'm the leader for 5 times 12, 60, a whole minute. I'm the leader. And so I can do whatever I want for that whole minute in terms of sequencing the transactions. That might be censoring people for the entire first 48 seconds and then sandwiching them all right at the end. It might be trying to manipulate oracles throughout that time period as the price on Binance moves. Obviously, like a minute or multiple minutes worth of proposer monopoly or like having someone in charge of all of the sequencing of Ethereum just feels like an absolute non-starter kind of out of the gate. There's some potential ways to address this. I won't go too much into them here, but yeah, happy to maybe take questions afterwards if people are interested. Right. Okay. Thanks for hanging with me. That was kind of the bulk of the kind of technical stuff. And now I think it's useful to just pause and really frame how this all fits in the broader landscape of the Ethereum design space. So I titled this section, Decentralization is the Means, Neutrality is the End, because really all of these design decisions are around preserving decentralization. And in my mind, the core reason for doing that is to preserve the neutrality of the chain. So this quote from Vitalik is from his Endgame, which he wrote in 2021. It's like a classic article, but his idea is that block production, this is kind of him looking forward into the future and what he predicts. Block production is centralized. Block validation is trustless and highly decentralized, and censorship is still prevented. So kind of operationalizing this into 3 design goals. Block production is centralized. This is just like an acknowledgement, a clear admission that MEV is going to be part of the system. Like this is a financial system. MEV is not going anywhere. However, we should try and encourage builder competition. So this multi-slot MEV thing that we described before is really a type of like rent-seeking behavior that builders can do to try and, make their drive their competitors out of the game. And so that's kind of one of the core things that shows up in these designs, is like, how can we make sure that the builders are all competitive with each other and that the auction is fair. Block validation is trustless and highly decentralized. I kind of take this as we want to limit the value of validator sophistication. So this is kind of tying back into these timing games and the value of being a validator in the first place. Like, the big picture of this whole talk is like, how are validators rewarded and why? We want validators to be rewarded like approximately evenly. So I should, as a home staker, I should get about the same rewards as I did if I joined Coinbase or a staking pool. Obviously, like, this is a very difficult thing to achieve, especially when you're considering home stakers have, are much more geographically decentralized. So they have kind of inherent latency disadvantages. They have less trust and reputation, so they're not able to make these deals with kind of corporate entities. And yeah, just generally, like, hardware and bandwidth requirements are going to be way lower running at home than running in a data center on like a super fast link and stuff. So in ensuring that there's kind of, I guess all of that's to say that there's no way validator rewards are going to be directly parity with these centralized providers, but kind of making the marginal utility for investing in validator sophistication very low is kind of how I think of this. It's like, sure, Coinbase can go and spend 10, $20 million investing in the fastest latency connections and everything, but that might only increase the rewards by like a few, like 10 bips or 20 bips or something like that, instead of it being like moving the rewards by like an order of magnitude or like a factor of 2 or something like that. So low marginal return on validator sophistication. And censorship is prevented. So this is actually the bit that I've talked about the least, but I think is the most important. And so that's kind of why I wanted to do this last section, and we'll talk about it a little more in the next slide. But fundamentally, I see neutrality as, these blocks are produced and transactions are included, and there's no real way that people can arbitrarily exclude and determine which transactions are included and which are excluded. So this is preserving the neutrality of Ethereum block space. We can kind of nitpick on the definition of neutrality here, but I think it's one of those things where everyone knows it when you see it. It's like, no one has an advantage if they're, trying to get a transaction or transfer included. It's included. And yeah, the kind of main focal point in my mind here is removing arbitrary transaction exclusion from this world. So as we showed at the beginning, 90% of Ethereum blocks go through this MEV boost thing, which means they're built by a small subset of block builders. And these block builders have an outsized influence in the protocol because they basically have total arbitrary discretion over which transactions they include and in what order. So the kind of fundamental question here is, okay, we have this decentralized validator set, but they're giving all this power to the builders. And in particular, they're giving the power for the ability to exclude transactions to the builders. How can we kind of bring back some of that agency to the validator set and allow them to express some preferences over the transactions that do get included? This kind of idea follows that, how about we have validators create what's called like a block template or an inclusion list that the builders have to follow. So I say, hey, I saw these transactions. You have to include them in my block. But beyond that, I don't really care. Like, you can reorder them, you can front run them, but you can't leave them out. I think that's fundamentally the core property of the censorship resistant design that I think is super important. And then the kind of direct follow on is this idea of, can multiple validators co-create this template? So trying to aggregate as much information from around the globe around what transactions people see and what transactions are valid and have to be included, without overly kind of restricting the builders. Because the moment you restrict the builders, you kind of push their power into different places. So there's kind of this idea of economic forces are there, and there's this like natural entropy in the system. How do you let the entropy express itself while still preserving the neutrality? And I think these like validator co-creation ideas are very much the way to do it. I had a slide going through it. I don't think it's worth doing too much because we're running a little low on time, but the idea, very high level, is that you have like a committee of people in this IL. This is an inclusion list. These are the block templates that we described. And they create these templates that the builders have to follow when they create the block. So that's it. We use the testers, or this like set of people to do some check that the builder is following the rules. But now we have basically this process where a bunch of validators are collaborating with the builder on producing the block. And this is kind of like a check and balance on the core property of transaction exclusion, which I think is the fundamental censorship resistance feature that we need to preserve. Cool. And this is my last slide. Yeah, this is kind of the personal take, but I think the most important and differentiating element of Ethereum is the digital property rights it exports. So the kind of inalienable right and the core promise that anyone in the world can store, send, and receive ETH. And kind of this permissionless store of value argument, to me, is still like what makes Ethereum fundamentally different from fintech, from the more centralized versions of crypto ecosystems. And so, yeah, that's kind of, again, this is why the decentralization and the kind of understanding validator rewards and how they could kind of playing through all the game theory of how they could centralize and concentrate economic power is something we do all the time. It's because this is the core promise we're trying to keep. And that's why we need the neutrality of the core chain to preserve that. So yeah, thanks very much. Happy to take questions. Again, this kind of line of research was something I wrote about in a piece called Meckenstein. There's a link down there. It includes the discussion on the block censorship resistance gadgets. So definitely take a look. And yeah, I think we're kind of right at 10 minutes before. So happy to stop here and take questions. I'll keep sharing the slides. If people have questions about specific slides, we can flick back and forth. But
yeah, thanks, Mike. So let me kind of start off, and we've got some good questions in the Q&A. So I totally get this idea of kind of smoothing the rewards and really focused on those that are kind of validating, and I totally understand how this kind of works towards decentralization. And I also see on the user side, this idea of reducing the probability of censorship is a good thing. But what this doesn't really address is maybe some of the downsides of the MEV, like the sandwich. So none of this would decrease the probability of a sandwich. Is that correct?
that's correct.
Yeah.
Yeah. And this argument actually becomes a really interesting one, and one that is fascinating because people are on completely opposite ends of the spectrum about it, right? So Phil Diane, who's kind of like one of the intellectual pioneers of the MEV space, he's the founder of Flashbots, wrote the original Flashboys 2.0 paper with Ari Jules and company. He actually views sandwiches as good things, right? He's like, this is good market efficiency playing out. Obviously, some other people would look at sandwiching, I think, especially from the traditional finance world. You guys are part of this world more than I, but would look at that and say, isn't that like illegal? Like you're front running people, like this is market manipulation. Yeah, so I didn't talk at all about kind of how can we actually reduce the overall sources of MEV. There's a lot of work being done on this kind of like app layer capture of MEV. So the kind of canonical example here is, instead of a Uniswap pool that trades kind of throughout the course of the block, what if you batch all those transactions together, you trade all the users against each other, and then you allow someone to bid for like the delta between the users' trades? So this is kind of like a coincidence of wants thing. There's other ideas around, how the MEV can be reduced. Some of them are actually, I think, worse in that like you push a lot of the MEV capture off chain. So Uniswap X, for example, just essentially becomes like an off-chain order book, like RFQ type system. It's not quite an order book because it's more like an RFQ thing, but it's like, well, we don't really have DeFi if we're executing all these trades off-chain. So that's kind of not the point either. So yeah, it's not a super clear answer, but I think I belong to the camp of people that thinks that like MEV is inevitable, and like, sure, we should and can do whatever we can to minimize it, but it's going to be a fact of life, and understanding that in the design of Ethereum's block space construction is like a pretty important thing.
Right. Okay. I guess I'm in the camp of we want the most efficient transaction process. And but yeah, so let me get to the questions, and let's start with Thomas, who's got a good question in terms of why not do this at the protocol level in terms of the smoothing?
Right. So all of these proposals are actually to do it at the protocol level. So I guess defining, let's look at the MEV burn example. I think it's probably the one everyone's most familiar with. So the protocol basically defines the rules of engagement between all these people. So the committee members are selected from the set of validators, and they're kind of incentivized to participate in this game because they're rewarded for doing the attestations and kind of doing this whole thing. So the smoothing that would take place in this MEV burn case is, okay, you're making sure that the bid is of sufficient value, and then at the protocol level, that bid, like the ETH that funded that bid, is effectively destroyed. And so it's kind of smoothed out across, people say it's smoothed out across all ETH holders. I don't know if I totally buy that argument, but it's more like, yeah, that ETH is no longer accessible by anyone. Obviously, the other way you could do this at the protocol level is you just say, hey, who are the validators that have been proposers over the last 1,000 slots? And you just take like a rolling window of the last 1,000 slots. You pool all the MEV in one bucket, and you kind of give out pro rata shares of to people who participated in the production during there. But yeah, all of these proposals are actually in the protocol and enshrined in the consensus mechanism that
Okay,
we've laid out.
very clear. Let me, Hassan Eldon's got a couple of questions that maybe we can combine. So one has to do like how often do the validators build their own blocks? And the other is what percent of blocks today are produced using MEV-Boost versus execution auctions?
Oh, right. Sorry. Yeah, I should have been more clear about this. So when I described MEV Boost and proposer builder separation today, that's the only system that's in production.
Exactly. Yeah.
And so this slide here shows the share of blocks that are built using MEV Boost, and it's like it kind of hovers right at 90%. So the kind of the I guess general understanding is that the other 10% of people are most likely building their own blocks. Of course, some people might be doing other things like having off-chain deals where they get their blocks built. But so yeah, about 10% of blocks are being vanilla builders here, or people who are building their own blocks. The other two proposals, execution auctions and MEV burn, they don't exist yet. They're kind of research ideas that try and address some of these concerns of MEV boost. But they're just that. They're not proposals. They're not in production. So the reason MEV boost happened out of protocol in the first place is really kind of an accident of history and more an engineering constraint than anything else. Like the merge was about to happen. This was September 2022. Everyone was very eager to get the merge out, but this was as MEV was coming onto the scene, and everyone was kind of understanding it more. And so as a result, Flashbots built this out of protocol thing, and everyone was like, okay, this is like a close enough approximation of something we want to do in protocol. So like, let's just do it out of protocol for now. Obviously, like the path dependence here is not great because now we have like a very entrenched set of actors who are used to MEV boost, and getting any change through is much more difficult, but that's where we're at today and why.
Okay. Thomas got a second question. Do we view builder activities as useful in some sense or purely toxic? It seems like the execution auctions are pushing volatility of rewards from proposers to builders.
Yeah, great question. So kind of two questions. The first question is, again, almost a perspective thing. It's like, okay, are HFT traders good or bad for humanity? It's like, I think they usually say, oh, we give really good tight spreads and good execution and these types of things. In the same way, I think you can argue Ethereum block builders do a lot of things that need to be done in order for the Ethereum ecosystem to have like a flourishing financial market, right? They do a lot of balancing of pools and price adjustments. They do liquidations of bad debt. So like if a lending protocol like Aave has a bunch of bad debt, it needs to get off the books. The only way to do that is to have people who are sniping it and know when it's coming and sophisticated in extracting it. So I think in general, what they do is very important. Obviously, the sandwiching stuff is where we get into this more gray area. There are proposals. There's ways you cannot get sandwiched. So for example, there's a lot of services that allow you to send a transaction instead of sending it to the public mempool. You can send it to a private mempool, like someone will keep the transaction secret, but allow people to backrun it. So they'll be able to go behind it, but they won't be able to go in front of it. This is like kind of in the vein of programmable privacy, or kind of like partial privacy. And I think those types of things are in the spirit of reducing the toxic behavior of builders and just kind of funneling the builder energy into the more pro-social stuff. Right. The second question was, I forget what the second question.
Yeah, it's so this kind of like shifting of volatility.
Oh, right.
Towards, yeah.
Yes, I agree. It actually does shift the volatility to the builders. And that's kind of one of the main concerns, is like, okay, the people best able to capture and trade on this volatility are going to be like one or two builders. But on the other hand, it's like, hey, shifting the volatility of validator rewards to the more centralized parties that we know are going to be centralized is like maybe an okay trade-off to make. So yeah, I agree with you, but it's not totally clear that that's a bad thing, at least in the, like, if the volatility exists in rewards, maybe it's better to have it on the builders who are well capitalized than to have it on the validator set. But yeah, definitely a great point.
Okay, Alfred has got his hand raised. Maybe we can unmute him for a verbal question.
Damn, I don't see him in here anymore, actually. I think he just dropped out.
Oh, okay. So let's go to Stefanos has got a question, and I'll read it. Different users / transactions generate different levels of MEV, but MEV burn treats users non-differentially. Is that a concern? Would MEV sharing, in which MEV is returned to the users who generate it, something that you would consider an alternative to MEV burn to mitigate this?
For sure, for sure. Yeah. So this is a really good point, and actually one that's coming up a lot lately when we think about kind of, you can almost cleanly partition transactions in the Ethereum space into MEV bearing and not MEV bearing, right? So swaps on Uniswap obviously have an impact on the state of the world and result in MEV getting exposed. A transfer from my cold wallet to my other cold wallet isn't doing any MEV for anyone. It's just like a tiny tip that I pay. Obviously there's granularities here, but the idea of rebating some amount of the MEV a transaction generates back to the user is a very kind of common one. And that's what's showing up in these kind of application capture, MEV capture protocols that we were describing before, like the coincidence of one stuff, Uniswap X. I still don't see them as mutually exclusive, these kind of rebating type things, as mutually exclusive with MEV burn, because I still think that there is going to be MEV exposed, and there always will be kind of differential amounts in terms of market conditions, just like naturally arising from the fact that there's this duration mismatch between Ethereum blocks and Binance. And so I think you can have a world where most of the MEV is captured by the applications and rebated to the users, but the remaining 15-20% of MEV that is kind of inherent to a financial system is burned. Like, I just don't think those two are directly in conflict. And actually, I think it's, I don't think MEV is going to have a silver bullet. So this kind of multi-pronged approach is probably the right way to deal with it. So yeah, that would be our response there.
Okay, so Mike, is it okay if we go just a few minutes over?
Yeah,
because
sure.
there are some questions. I see Katya has got her hand raised for a verbal question.
Sorry, that was a mistake.
Oh, the raising of your hand. Okay. Okay, so let's go to Giorgio's question. In execution auctions, how can builders bid efficiently since they don't know what they are bidding on ahead of time?
Super good question. So they don't know the block contents, but they do know what they're bidding on, which is they're bidding on the right to produce a block 32 slots in the future. So instead of bidding on a specific block and a specific state of the world and a set of transactions and a price on Binance, which is what you're doing if you're doing a just-in-time auction, you're actually bidding on like how much MEV you think you'll be able to extract on average from a slot 32 slots in the future. Now, this still could have still could be alpha here based on the time, right? Like, let's say the great example of this is like, let's say, in 32 slots, there's going to be a massive NFT drop, right? Now you want to be the person building the block, because if you can get all those NFT transactions, they're going to pay a ton of tips. Now you have some alpha, that this is going to be valuable, but obviously there's other people that might have the same alpha. So you do know what you're bidding for. Just the object is kind of less deterministic and more probabilistic. Now, this kind of bears the question of like, who does this benefit to have an auction that's more probabilistic than deterministic? It probably benefits the best block builder differentially, right? Like if I on average can extract the most MEV from each slot, then I'm going to win every single auction, right? Up to like capital constraints. So I just win all the auctions, and then I only resell at a premium if I think that there's some chance that someone else will have a higher value than me. So like there is this kind of this problem you describe as far as this differential access to the auction winning. But I think the object is well known, and you just have to be clear that what you're buying is not necessarily as deterministic as it would be in the just-in-time version.
Yeah, so Fahad's got a good point on this, that if you bid ahead of time with very little information, then you could just resell. And doesn't this just collapse to the old system?
Yeah. Yep. And that's mainly the argument that Max and Malesh make, which is in this paper here, which is, yeah, you buy all the slots ahead of time and you only resell at a premium. And then you basically rent seek on your monopoly of all the slots. This is certainly kind of the core issue. I think this is addressable by having, this is where the Meckenstein thing comes in. And it's called Meckenstein because it's a portmanteau of mechanism and Frankenstein. You're just smashing a bunch of stuff together. But the idea here is if you sell the block ahead of time, but then you do a just-in-time auction for the top of the block, which is the most valuable portion of the block, then you can actually constrain the builder's behavior and force them to compete in the real-time auction just in time as well, even if they bought the slot ahead of time. So effectively what you're doing here is you're partitioning the block into two halves, and you sell the bottom half 32 slots ahead of time, and you sell the top half just in time. And now this is kind of this weird, complicated double auction thing, lot to unpack in terms of the complexity there. But this is all to point out that I don't think the execution auctions is just dead on arrival. There's things you can do to make it more competitive at the real-time level.
Okay, great. So we are a little past our promised time. This has been very enlightening. I really appreciate you taking the time to talk to us. And thank you.
Yeah, thank you all. Appreciate you.